Okay, good afternoon, everybody.
Afternoon, sir.
Afternoon, sir.
Afternoon, sir.
Okay, so how is everybody this evening?
Tired, sir.
I can imagine in your case that you must be very tired, yes. But everybody else seemed to be okay.
Not bad, sir. Not bad.
Not bad. Okay, good. All right. This afternoon into evening, we will be looking at single phase transformers. So we're just gonna be looking at some preliminary material on it, and we do probably a couple examples. So I don't expect that we'll be here for the 2 hours, but we'll see how it goes. All right.
You're going to let us discuss the test after we finish, sir.
Which test?
So I think the test is scheduled for next week, mid-semester.
Oh, yeah, man. Whatever you want to discuss, I'm open.
All right, sir.
All right. Just remind me if I forget. But yes, the test, maybe we should start here. The test is gonna be next week this time, and we will cover units 1 to 4. No, I won't include unit 4. Units 1 to 3. So yeah, we're starting unit 4 today. We probably wouldn't have anything challenging from unit 4 to give you anyway. So units 1 to 3. And when I say challenging, I'm just trying to make it look very difficult, but it's usually a very easy exam. So you shouldn't worry. Units 1 to 3, we will cover. Maybe to do the test will probably be somewhere between an hour and an hour and a half. You will get more details maybe by the weekend, but you can block out in your mind an hour to an hour and a half for the test. So we will do it online in the sense that I will send you the test and you do it under my observation, and then you submit by a specified time. So you'll get a few minutes to submit, so you don't have to worry about anything except make sure that you study and are on top of your game. All right. Okay, Mr. Chambers.
Yes, sir. Sir, and the next thing, sir, the earlier the better, because a few of us have a test immediately after that at 7 o'clock next week.
At 7 o'clock. Oh, okay. All right. So, all right. Maybe what I could do then is make it an hour, and we start as soon as possible. Persons, I mean, even up until this time, and not everybody is in the class. And usually every week we wait maybe about 10 minutes before we start, and usually we don't have half the class. So when we start, and whoever is late is just gonna be late. All right. So I will bear in mind that you have another test after after mine, so we'll maybe make it an hour to give you enough time to submit and then relax yourself for the next test. Reasonable?
Yes, sir.
Okay. All right, so let us start with single phase transformers and we have practically been looking at it started from last week when we did mutual inductance. But we'll look at it more formally now. So you may see these equipment on poles near on the road. So these are the transformers. So this would be what is called a pole mounted transformer. And typically the voltages on the primary side, so the primary voltages would be connected on this side up here would be 13.8 kV or 12 kV or 6.9 kV in Jamaica. And on the secondary side, you will have 110 or 220. And you know what transformers are. So they normally just generally raises or lowers voltage from one level to another. So we were talking about 13.8 kV on the primary side. And on the secondary side, you'd have 110, 220, that kind of thing. So transformers transform voltages from one level to another. So it's not really an energy conversion, it's transforming voltages from one level to another, or currents from one level to another. All right, so we have been introduced from maybe high school to this diagram for a transformer. But you learned last week that this is really just a kind of artist representation or a simplified representation of what is actually happening inside, especially the larger transformers. But this is a two-winding transformer. You can have windings with, you can have transformer with a primary, a secondary, and a tertiary winding. Normally, you don't hear more than tertiary windings, but this is a two-winding transformer. So it has a primary, and then the primary now would be connected to a supply voltage, and it has a secondary winding, which would be connected to the load. Now, bear in mind that any one of these windings could become primary. Once it's connected to the supply, it becomes a primary winding. All right, so it doesn't have to do with voltage that makes it primary, right? It's where the supply is connected. So the primary winding would have the supply voltage connected to it, and the secondary winding would have the load connected to it. All right, and as we have learned, the transformer core is made up of some kind of ferromagnetic material. And we have been looking at that from unit 2 when we did magnetic circuit. So you'll remember this kind of magnetic circuit also. Now there are generally two types of core construction, and I want you to do some work on that. So that's what's down here in red. But typically the two types of construction are the core type and the shell type. So I want you to go and research and get diagrams of what the core type looks like and what the shell type looks like, and make a note of them for your future reference. All right. Now, the core is actually made up of laminations. So very small slices of metal are actually put together to form that large mass of core. And the laminations have different shapes. And the shapes look like these letters: E, R, I, R, L, or U, right? So you can also do some read up on those, the different type of laminations that you can have. Right? And the importance of laminating the core, as you would all know, so I won't even bother ask, is to reduce the eddy currents that will be flowing through the core if it was one solid piece of metal, and the hysteresis losses that would take place as the flux is alternating across the core, right? So the laminations are basically there to reduce losses, and the losses would manifest itself in the form of heat. So normally a transformer that is energized will be emitting some kind of heat. So if you, especially the large power transformers, if you're nearby, you will actually feel the heat. And because of this kind of heat, the heat can cause damage to the windings. So methods of cooling the transformer exists. So there are different methods of cooling the transformer, which is something that we'll get into later.
Sir.
Yes, sir.
Student is saying the host keep kicking him out of the meeting, so he can't get him.
Say that again?
A student, Mr. Allen, is saying the host keep kicking him out of the meeting. He's trying to get him.
Mr. Allen?
Basically. Yeah.
Or if him come with an alias, I might not know it. So maybe that's the problem.
Okay.
That's Romario Allen?
I'm not sure, no, sir. I know it's Allen.
Okay.
Yes, sir. That's his name.
Okay. All right.
I'm so tired.
All right. Time to try again. All right, let me see if I can get him back. All right. So I want you to as I said, look at the different type of construction and the different type of laminations. All right, so for the ideal transformer, So yeah, up until now, you have been only introduced to the ideal transformer. So from high school up until this point, you have only been introduced to the ideal transformer. But the ideal transformer have some characteristics that you need to be aware of. One, it has very low reluctance, which means then that it allows flux to pass through it very easily, right? High permeability also goes with that, right? So low reluctance, so very low magnetic resistance to the flux, and high permeability means that it allows flux to pass through very easily. The ideal transformer also has no leakages. So notice now that no leakage flux are around here, right? And I have asked you to look up fringing. There's no fringing also. All right, so the path for the flux is uniform right through. All right, with it now, a very small current. So Hughes described it as a vanishingly small current is required to establish this magnetic flux. So you don't need a large current, and you will see when we're working out some problems that it's a very small current that is required to establish the magnetic flux. All right. The winding impedances. The winding impedances are non-existent, so the wires don't have any resistance or reactance in theory. That's the ideal winding, and that has some consequence, right? So no resistance. So no, if there are no impedances, there are no voltage drop across the winding. Right. All right, so let's get into the principle of operation now of the transformer. We connect a supply voltage V1 to the primary winding, and because this is now a closed circuit, a current will flow in the primary winding. All right. That current will produce a flux. Right? So you know, associated with any current is a flux. Now this current here is an alternating current. So the flux therefore will also be alternating. Now as this flux in this ideal transformer cuts the winding, so it will be cutting both the primary and secondary. And remember we said that in the ideal transformer, there's no leakage. So all the flux that is produced here by coil 1 will be linking coil 2. No, because there's no leakage, as I say, all the flux links both coils. So this is a mutual flux. Right. Now as the flux is alternating, according to Faraday's law, it induces an EMF across each of the windings. So an induced EMF develops across this primary winding, and that will be E1. Another induced EMF develops across E2, across winding 2, that will be E2. Now, on the ideal situation, since there are no voltage drops across the windings, V1 and E1 would be equal in magnitude. All right, and this comes from what we did before with Faraday's law and also Lenz's law. So V1 and E1 would basically be equal and opposite in magnitude, in sign, sorry, but they would have the same magnitude. All right. On the no load situation, E2 and V2, the terminal voltage, would also be the same. All right. But once there's a load connected to the secondary winding, our current will start to flow. And then you will have load current flowing through on the secondary. That will also produce its own flux, but we won't get to that yet. All right, so we're looking at the basic situation. So to reiterate, a primary winding, a supply is connected to it. Because it's a closed circuit, current will flow through it. That current will produce a flux. And that flux will link the secondary winding. All of the flux produced by the primary winding will link the secondary winding in the ideal situation. And the flux is a varying flux. It varies just at the same rate as the current is varying. So you have an induced EMF across each of the winding, and that induced EMF on the secondary side would be available to supply a load. All right, and once a load is connected, then a current will flow in the secondary winding also. So under no load, there'll be no current in the secondary winding. All right, this is something for you to do. We want to prove that the induced EMF, let me go back to that. These induced EMFs, E1 and E2 are related to these formulas. So this is something that I want you to do. I'm going to give you maybe about 10 minutes or so to try to prove them. All right, but this is what you will be using to come up with these equations. Given that E, the induced EMF from what we did from last week with Faraday, N d phi by dt. So E is equal to N d phi by dt, and we know that phi is sinusoidal. So remember we said that the current is sinusoidal, so the flux is going to be sinusoidal. So the phi is given by this equation, phi m sine omega t, where omega is equal to 2 pi f. So I want you to show that any one of the induced EMF that you want to choose, E1 or E2, so it would be equal to these relationships here. So E1 is equal to 4.44 F N1 phi m, and E2, as you see here, 4.44 F N2 phi m. And this is where we start, right? With all of these conditions here. All right. So I want you to spend a few minutes to prove that E1 is equal to that or E2 is equal to that. Any one of them you want to choose. And E1 and E2 are the effective RMS values. All right. So spend a few minutes and see if you can prove these for me. Okay. No response?
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
All right, good.
So the person still hasn't gotten in yet, and I'm not sure what is happening.
Let me check with him. What's his email?
Sir, you can go back to the PowerPoint, please.
Any success yet?
No, sir.
No, sir.
Any progress at all?
Yes, sir.
Mr. Buchanan, I didn't get that.
Yes, sir. I get up to changing the D or changing the phi to phi ms sine omega, differentiating it, getting omega phi m cos omega t, then taking the max value. So max value of cos would be 1. So E max would be omega n phi m, sorry, omega n phi m, and then you divide that by square root 2 to get the RMS value.
Okay. Impressive, man. Impressive. Yeah, well on top of your maths game. Anybody else? Anybody else making some progress? Anybody followed what Mr. Buchanan was saying?
Yes, sir.
Okay, good. That means that you're near completion then.
Sir, I think there's just one part of it that I can't explain fully. So.
Oh, which part is that?
Sir, the part with the sign. After you change the omega to 2 pi f. Yes, sir. To the 2 pi f. I don't remember what the trigger identity is to change that.
Oh, okay. One we are dealing with that is to do your substitution at the very last minute. All right, so I'll give you a couple more minutes and then let's see. Ah, I actually showed you.
So we weren't looking. You want to show us again?
All right, I will do that. All right. Anybody else?
Sir.
Yes.
We do something, but they actually arrive at the answers, but I don't know if one would be really legal.
All right. Well, explain why you did so. Make we say it's illegal.
All right. So d5 by dt, if you differentiate that, first you get omega phi m cos omega t.
Right.
but omega is 2 pi f. So f is 1 over t. So t times 1 over t is 1. And that leaves you with omega phi m, right? And the formula now, the first formula, n.
Cos what? Cos 2 pi.
Cos 2 pi is 1. Yeah. So you live with cos 2 pi, and cos 2 pi is 1. So that leaves you with omega phi m. And yeah, after that though, you have E is equal to n d phi by dt. So you just multiply the n, you end up with n phi m omega n phi m. And that would be E max. Sorry, n, that's not one. Yeah, you end up with n phi m 2 pi f. The cos omega was I'm not sure where I mix up this up. Let me go again. So d phi by dt is omega phi m cos omega t. Right? Oh yes, this is where I'm left out. Yeah. So 1 over t is the same thing as f. So if you multiply f by t, you get 1, and then you're now left with omega phi m 2 pi. Omega phi m 2 pi. 2 pi, yeah, right. And now n d phi by dt, if you multiply it out, you get n phi m 2 pi f. And that is equal to the E, maximum E. And if you divide all of that by root 2, the 2 pi f divided by root 2 is 4.44. And that is how you get the n phi m f. 4.44 n phi m f.
Okay. All right. Yeah, generally that can work too. It works out mathematically how you do it. The only hesitation I have is that, well, t will always be cancelled, right? But the cosine is not always at a maximum value. So yeah, when you cancel t with 1 over the f 1 over t, yeah, then that cancels out. All right, so yeah, that can work. This is another way I think Mr. Buchanan did it this way also. So what I have in here in red is what he did. So either method can work.
I prefer your method, sir, because we're still not so clear 100% on right. I prefer your method, yeah. We learn it.
Yeah. You know, that is also, this is something that I've asked in previous time for people to prove to, you know, so I guess you can probably make a note of it. All right, so basically what we're doing now is substituting the phi m sine omega t into the Faraday's equation for the induced EMF. And since phi m is a constant, we can take it out at the differential. I keep getting some names that I'm not familiar with at all. So kind of hesitant to bring in people who I don't know. All right, so anyway, So if I differentiate d sine omega t by dt, then we get n phi m omega cos omega t, and then E1 would be equal to N1. So if I know, so this is the general equation for E. If I want to use it for the primary induced EMF, E1 would be equal to N1 phi m omega cos omega t. Now this part of the equation is the cosine function. And what we need to do though is to find the maximum value of E1, right? So the maximum value of E1 occurs when the cosine function is equal to 1. So the cos omega t part is equal to 1. All right. If you remember the sine or the cosine wave. By the way, the cosine wave is also the sine wave, but shifted in time and space. All right, so the maximum value for the cos omega t part of this equation here would be equal to 1. And then therefore E1 max would be equal to N1 phi m omega. And then the RMS value is the E1 max divided by √2. And that works out to be that. So here now you put the pi as 22/7 or 3.14, and you work out and get this value 4.44 f N1 phi m. And we could also write it for E2. This time now you use N2. All right, so 4.44 f N2 phi m. All right, so so yes.
So in terms of diagrams for this question, what would you draw?
I would actually draw a sine wave, you know, or the cosine wave. And yeah, that reminds me. If I was actually in class, I would have drawn the wave before I asked you to solve the problem. I would draw the wave, but I wouldn't say anything to you. So I would draw the cosine wave with a maximum value of 1, right? So you would actually see now that the cosine, the maximum value of the cosine is 1. For in terms of, you can also draw the induced EMF now, similarly, but no, that its magnitude, its maximum value now would be this part here. Right. All right, so you could draw a similar equation, a similar graph for E1. All right, so it would still have the same cosine shape. All right. Some other equations for the ideal transformer. The turns ratio, N1 over N2. And please note this, the turns ratio is the primary winding turns, the primary turns divided by the secondary turns. So N1 over N2. Not the other way around, because I know you will see it on the internet as N2 over N1, but that is incorrect. The turns ratio is the primary turns divided by the secondary turns. All right. Now, if I divide these two equations, E1 divided by E2, you'll notice now that what remains after the cancellations would be N1 over N2. So I have another equation for the turns ratio. A would also be equal to E1 divided by E2. E1 divided by E2 would also be called the voltage ratio. Right. All right, so we had spoken about, so it's an ideal transformer, so there are no voltage drops across here. So E1 would be equal to V1 in terms of magnitude, since there are no drops across here. And hence I can write the turns ratio in terms of V1 and V2 also. All right, and V1 now would be the primary voltage, supply voltage, and V2 would be this, the secondary terminal voltage. So I'm coming up with different ways of writing the relationship for the turns ratio. All right, now what happens if we connect a load to the secondary side of the transformer? All right, you'll remember something called MMF that we looked at a couple weeks ago. All right, so the flux that is produced here is actually produced by an MMF, right? By the current I1 through turns N1. So that is what is the source MMF of this flux, right? Right. Now this MMF is gonna be dropped across the secondary winding. So this is the total flux in the system. It's gonna be dropped across the other winding. Right. All right, so that MMF is also equal to, now that a load is connected here, we have a I2 times N2. So that MMF is also equal to I2 N2. So MMF is equal I1 N1 and is also equal to I2 N2. Now we remember that N1 over N2 is our turns ratio. So if we group the terms in N, so bring N2 over here and bring I1 over there, we have N1 over N2 is equal to I2 over I1. So the turns ratio, again, A would be equal to N1 over N2 equal to I2 over I1. It's equal to E1 over E2 and also V1 over V2. All right, so a lot of relationships for the turns ratio. All right. All right, so there are some other things that you need to know about the transformer. Normally the transformer is described in terms of its nameplate rating. So these are usually, so it is usually described in terms of its apparent power rating and the primary and the secondary voltage rating. So there are other things that describe the transformer, and later on we'll get into some of those also. All right, but this is generally how you'd see a problem written. So you will see the apparent power rating given and the primary and the secondary voltage under normal conditions would be given also. All right, so remember S now is not reluctance, but apparent power when we're dealing with the transformer, and the unit is volt amperes. Usually our units are kilovolt amperes or megavolt amperes for large power transformers. And S is given by V1 I1, and it's also equal to S. Remember S now, apparent power. So apparent power, which is similar to the DC power now, would be V times I. All right. So when you think about apparent power, think about the relationship that you would have for power when you're looking at a DC circuit, right? So apparent power V times I. And it will be V1 I1, and it's also, so same rating on either side of the transformer. So S would also be equal to V2 I2. I could have used these two relationships here, I2 over I1 equal to V1 over V2. And so imagine that E1 over E2 not there right now. And if I cross multiply, I get V1 times I1 and V2 times I2. All right. And then that would give me the apparent power relationship. So V1 I1 equal V2 I2. All right. I1 is the primary current, of course. I2 is the secondary current. Now, from what we did before, when we were looking at three-phase systems, the real power, P, is equal to S cos theta. Everybody remember that? Anybody remember that? So the real power or the active power is equal to the apparent power times the cos theta. All right. I remember Mr. Atkinson asking me, I think it was Mr. Atkinson, what is cos theta in practical terms? So you can see it here again, the P divided by the S. So the actual power that you get out over what you think you put in, right? All right. Now, if you look at this circuit, P1 real power is equal to VI cos theta. So the input power then would be V1 I1 cos theta 1, and the output power would be V2 I2 cos theta 2. Now, cos theta 2 is the load power factor. So you should bear that in mind. Cos theta 2 is the load power factor. That is usually different from the power factor on the primary side because there's some slight differences between the phase angles for the current, the primary current and the secondary current. So the power factor angle is not the same on the primary side, right? But bear in mind, cos theta 2 is the load power factor. All right. So we're gonna leave the ideal for a little while. And I will show you a picture of what the exact equivalent circuit of the transformer looks like. So just to give you a picture, so that the ideal that we had before is not exactly as we had it. But the ideal is still represented in this exact equivalent circuit. So if you notice this part where you have the bracket here, the curly bracket, this would be representing the ideal. All right, next time I'll put some dotted lines across here. All right, so yeah, this part here where you have E1 and E2 will be representing the ideal transformer. But then you have some other parts. You have the winding, which has its impedance. You have the core, which also has its impedance. And the secondary winding has its own impedance too. All right, so trying to get you introduced to the fact now that the transformer actually has some other parameters that we need to consider. All right, so Z1 here would be the primary winding impedance, and that's composed of R1 and X1. And the secondary winding impedance would have R2. So the windings now, and this is the winding we're talking about, have impedances. Resistance. So yesterday, those who did lab 3, well, all those who have done lab 2, when we did the iron core coil, you were measuring the winding resistance. When you measure the resistance of the winding, you were measuring the winding resistance for the primary winding. All right. Later on, when we get to lab 4, we'll actually be determining these parameters. The winding impedance and the core parameters. We'll be determining those in the lab. All right, so let's talk a little bit about the core. So the core in this diagram is represented by the parallel branches. R0 and X0. All right. Normally, I call them RC and XM. So you'll find that in other textbooks. So RC and XM. So RC would be the core loss resistance. So note the term core loss resistance, right? So it's a resistance of the core material. And basically this is representing the losses that is taking place due to eddy current and hysteresis. Right? So the core loss resistance, which accounts for eddy current and hysteresis. And XM, or XO here, is the magnetizing reactance. Right? So associated with the core also is a magnetizing reactance. Remember, when we put a current in the winding, a magnetic flux is created, and that flux will be flowing through the magnetic core. All right. Now that current that produces the flux actually lags the voltage supply by 90 degrees. Right? And hence, we know that there is an inductive reactance that current is flowing through, right? So that's why we have an X here now to represent that magnetizing branch of the core. All right, so it is what is actually responsible now for producing the flux. Well, the phase lag between the flux and the voltage. All right. Now, let me go back here. So notice that there is an I0 here too that is called a no load current. No load current. And I should tell you something about this no load current. It exists whether there's load on the transformer or not. Once the transformer is energized, whether or not there's any load, a current will flow through here to supply the no load power loss. Right? So it will supply the core loss power, and it will supply the magnetizing current that will create the magnetic flux. So you need that current will produce, it has two components, one that supplies the eddy current and hysteresis losses, and the other that provides the magnetizing flux, right? So, all right, that current I0 now has two components. IC, the core loss current, and IM, the magnetizing current. So I0 is core loss current. So it's the vector sum now of the core loss current and the magnetizing current. Right? Now notice, since IC is flowing through this resistive section of the core, we know that for a resistor, the current and the voltage are in phase. So IC would be in phase with the supply voltage V1. But IM lags the voltage, the supply voltage, by 90 degrees. So hence we know that there's this inductive reactance. Because we're inductive reactance, the current lags the voltage by 90 degrees, right? And the flux is going to be in phase with this magnetizing current, right? This magnetizing current is what produces the flux. So the magnetizing current and the flux are in phase. All right, the resultant of IM and IC give you the no load current, right? And this power factor, this angle here is called the no load power factor angle. Yeah. So no load power factor angle. And that's the angle between V1 and I naught, the no load current. So no load power factor angle between the supply voltage and the no load current. All right. Any question there?
Go over that one more time, sir, the last part.
All right. All right, let me go over this. All right, so the no load current. So when you do the no load test on the transformer, Conroy, we actually measure this current, the I0, right?
Right.
That I0 though has two components. One that supplies the heat in the transformer, the eddy current and the core loss. The core loss.
I squared R.
No.
R losses.
Well, in the core, no, it's not. So it's not I square R, although that relationship can work, right? So it's in the core though. So when I thought about the R a while ago, I was thinking winding, but it's the core. So it's the I square R in the core. So the core basically can be considered as partly resistive, right? That part that consumes the eddy current and the hysteresis. So IC now would be supplying that eddy current and hysteresis. All right. So part of I0 is IC. And IC would be what is responsible for the eddy current and the hysteresis. Part of I0 is also IM, the magnetizing current. Right? And that magnetizing current is what produces the magnetizing flux. The flux that will flow through the core, IM is what produces it. So although I0 is a very small current, it has two components, right? Part that produces the flux and part that supplies the core losses, the eddy current and the hysteresis. Now, because core losses now can be considered resistive, IC and V1 are in phase. So notice now this is a phasor diagram now. All right. So IC and V1 are in phase, but IM lags V1 by 90 degrees because of this XM here. All right. So IM will be flowing through XM, and therefore IM would be lagging V1 by 90 degrees, but IM is what produces the flux. So IM and the flux are in phase. All right, so notice that they are same angle, same horizontal line. All right. I didn't mention E1 and E2, but E1 would be equal and opposite to V1, right? And E1, E2 could be either in phase with E2 could be either in phase with E1 or, depending on how the transformer is wound and the polarity, are in phase with V1, right? In this case, they draw both of them in phase here. All right. All right.
So no in between, sir. Is either one or the other?
Which one are you talking about?
E2 is either in phase with E1 or V1. It can't be in between.
So it depends on the load into, right? On no load though. On no load, they would be in phase. On no load, they would be in phase. Right. All right. So no, on no load.
All right.
All right. Good. All right. Now, if I look a little bit more in depth at the diagram, I can come up with some relationships. So the cosine of this angle here would be what? Adjacent over hypotenuse, right? So that would be IC over I0. So I can write, make IC the subject of the formula now. So IC would be equal to I0 cos phi 0. Right? Remember, phi 0 is a no load power factor angle. And I can write a relationship for IM here also. So IM would be, so this is IM, but we could translate it up here. And then sine of this angle would give me opposite over hypotenuse. So IM would be equal to I0 sine phi 0. All right. And if you use Pythagoras, I0 would be equal to IM square plus IC square, and you square root of all of that. So this is Pythagoras going here now, either here or here. All right, the 90 degree here. All right, so I0 square is equal to IC square plus IM square. All right, of course you can also write them as vectors. So all right. All right, so the Coriolis power, we have been talking about the Coriolis. So you have a Coriolis resistance, you have a Coriolis power. So the Coriolis power now would be V1 times IC. So it's V, and substitute for IC is V1 I0 cos phi 0. All right, so the Coriolis power is given by this V1 I0 cos phi 0. All right, and as before, cos phi 0 is a no load power factor angle, and PC is the Coriolis power. All right, so this is one relationship. So as Conroy pointed out a while ago, we could have said IC square RC also, right? Or V1 square over RC. So all of the relationships that you know for power in a DC circuit, we could write them for this part. But since it's an AC circuit, we want to include the power factor, right? All right, so let's look at a little example. All right, so this says that 3,300 volt, 440 volt single phase transformer takes a no load current of 0.8 amps and the iron loss is 5,000 watts. So the iron loss is the same thing as core loss. So make a note of that. Iron loss is the same thing as the core loss because the core is made up of iron. All right. So we should draw the no load phasor diagram, which is this, right? I don't know if it's drawn to scale here though. I just give you a diagram. But in this case, when they say draw the no load phasor diagram, you should draw it to scale relatively and determine the values of the magnetizing and core loss components of the no load current. So basically they wanted to find IM, the magnetizing component, and the core loss component would be IC. So they wanted to find IC and IM. All right, so from the data that given, V1 is equal to 3,300 volts. I0, the no load current, is equal to 0.8 amps. So notice, look how it's small. So look at the high voltage, 3,300 volts, and it just pushes a 0.8 amps through the primary winding on no load. I think when we in the lab, the current probably won't go more than 1 amp. Somewhere around there. So, and the core loss power is 500. So we can use the relationship that we know for PC, the one we had from before. PC is equal to V1 IC. I'm going too fast. All right, so PC is equal to V1 IC. So therefore, IC is equal to PC over V1. And that's a 500 over the 3,300. So 0.152 amps, practically. And then the magnetizing current can be found from this. You could use other relationships, right? The other ones that we mentioned before. Right. So once you find IC and you have I0, you could work out what cos theta is. Then you could work out what theta is, theta 0. And then you find sine of that. So longer process, right? So we always look for the quickest way to solve our problems. So IM would be the square root of this. I0 square minus IC square. And that ends up at 0.786 amps. All right. Any question on that? So remember, if you were to draw to scale now, then you would see that IM would be about 7 times the value of IC. Right? So IM should be longer by about 7 times, 6 or 7 times what IC is. So if I ask you to draw something, I will be looking for that kind of proportion. I mean, it doesn't have to be ruler exact, but I need to see that kind of
some form of difference.
Major difference, right? Right. All right. I think this might be the last one. I don't think I gave you any homework. Yeah. All right. So right. All right. So this is another question. All right. So this time you're given the power rating, the apparent power rating. Sorry. So a 50 kVA single phase transformer has a turns ratio of 300 to 20, or 300 over 20. The primary winding is connected to a 2,200 volt 50 hertz supply. Calculate the secondary voltage on no load, the approximate values of the primary and secondary currents on full load, and the maximum value of the flux. All right. So picking out the data, V1 is equal to 2,200 volts. S is equal to 50 kVA. So 50 times 10 to the 3 volt amperes. And A would be N1 over N2. And N1 over N2 is also equal to V1 over V2. And we got the ratio from before, 300 over 20. And so 300 over 20 is equal to 15. So A would be equal to 15. From this relationship here, V2 over V1 would be equal to 15. So if I move V2 up to here and 15 down here, I get V2 would be equal to V1 over 15. So it's a 2,200 over 15. And hence V2 is equal to 146.67 volts. All right. Any question on that? Or straightforward?
All right, sir.
All right, good. All right. B now asks us to find the approximate values of the primary and secondary currents on full load. And remember, there's a reason why they say approximate, right? Because in reality, there would be some voltage drop. So we wouldn't have these. So remember, these relationships now are based on ideal. But this S relationship is based on ideal, right? And we would use it when we would use the S relationships when we want to find the currents for different ratings, or load ratings on the transformer. All right, so I1 is S over V1 from this part here.
Yeah, you can repeat that series about the S, sir.
S is the apparent power rating, right?
Yes, sir.
And it is the same on both the primary side of the transformer or on the secondary side. So the apparent power rating would be given by these relationship. All right, V1 I1 or V2 I2.
All right, sir.
All right, so normally whether the transformer is ideal or not, we will use the apparent power rating to determine what the currents are. With me? Whether the transformer was ideal or not, we use the apparent power rating now to determine the magnitude of the primary and secondary currents. All right, so I1 would be S using this part of the relationship, S over V1. So it's 50 times 10 to the 3 over 2,200. And I get 22.727 amps. And I could use this now to find I2 S over V2, and it's 340.91 amps, right? Or I could have found it also using the turns ratio. So I2 is equal to A times I1, and A is 15, so 15 times the 22.72, and gives me that 340.91 amps.
Yes, sir.
Yes.
Wouldn't V2, the 146.67 volt, represent the no load voltage, and B also are full load?
All right, so we're looking at the full load current now, yeah. V2 actually is the terminal voltage, right? The terminal voltage. So, very good question. The terminal voltage is supposed to be what the transformer is rated for, right? So what it's rated for is what you will actually get out. So the voltage that is on the, let me go back to this one. Right, so the 440 here is what the transformer should deliver at full load. With me? Now, E2 might be different from the terminal voltage, right? So E2 might be different from the terminal voltage, and you will see that when we start to do some problems with loading the transformer. But the transformer, the S1 is the primary input voltage, and V2 would be the secondary output voltage. All right. So again, if you have a light bulb that says 110 40 watts or 120 volts 40 watts, it means that you will get 40 watts when 120 volts is applied to it. So your socket should be giving you 120 volts. So you can get your 40 watts out of it. You with me? So at your home, your outlet should be giving you your nominal voltage. All right. So for example, 120 volts. The transformer though, or maybe what comes into your house at the meter it would be higher than the 120 that you get, because you're going to have some voltage drop inside of your house, and they have to account for the voltage drop to make sure that your equipment, which are rated to get 120 volts, will actually get 120 volts. You with me?
Yes, sir, somewhat.
Somewhat. All right. I think it will become a little bit clearer. So, equipments have voltage ratings, right? So your appliances have voltage ratings. So that is what they are rated to get. So the transformer that is supplying your house will make sure that you get the what you should be getting at your house, right? Now, JPS actually has a tolerance within which they operate. So they operate within plus or minus 6% of the nominal voltage that you're supposed to be getting. So anywhere between +6 and -6, your voltage can actually be by law, right? So you're getting that, but it doesn't mean so that is actually what comes into your house, or what comes into the meter. You might be getting higher there, but you will have some voltage drops in your circuit, or even from the transformer coming down, right? So there's a difference between E2 and V2, which we'll get into later on, right? But for now, just take it that the secondary voltage, right, is what we'll be using to determine the apparent power rating on the secondary side. So V2 times I2 will be giving you this, right? And this is rated at, this is what you should be getting out of the transformer on load, right? So when the transformer is loaded, this is what you should be getting out, all right? All right, so in the problem that we are solving, we were now asked to find that one. So the apparent power will help us to find it. All right. And any other question on that? No.
So my take on it, sir, was just the seeing that in part A, you calculate the no load voltage to be 146.67 volts.
Yeah.
And in B, it asks for the secondary current on full load. So I'm taking that the voltage you use in B is also the no load voltage, which is the one for I2, which is the RV2, which is the 146.67. So I'm not sure if it's a word, it's confusing me or what, but I'm just saying.
No, you're no man, you're okay. What I probably need to do though is to go back here. All right. So right now the transformer is ideal, right? The transformer that we're looking at is ideal. So there are no winding losses there. With me? So the problem that we are looking at right now is looking at an ideal transformer that only has core parameters. So there are no winding losses. So there are no winding impedance on the primary and no winding impedance on the secondary. So E2 and V2 in that case would be equal, right? So on no load, E2 is equal to V2 on no load. But on full load, we're saying also, because there are no drops across here in the transformer that we're looking at now, E2 and V2 are still the same.
That's ideal.
Right, ideal. Right, so the problem that we're looking at now, there are no winding losses at all.
Okay.
All right. So yeah, we're looking at the ideal. When we start to look at the more practical ones, yeah, we will give you values for impedances and things like that. All right, so again, now remember now that again, ideal E1 is equal to V1, an ideal situation as we had showed before. So E1, we had derived this. E1 is equal to 4.44 FN1 phi m. Could have also used E2, right? So for this ideal transformer, E1 is equal to V1. So no winding loss on the primary side. Right? So E1 is equal to V1. And E1 is the 2,200. And we divide it by this 4.44 F. F was 50 hertz. And N1 was a 300 here. Right. So phi m is equal to 0.033 Webers. We could have also found phi m from the equation for E2. So you can also try that. Right. I should get about the same answer here. All right. So when you questions like this and there are no impedances provided, basically are talking about the ideal situation. Right. The question that we did before has moved a little bit away from ideal. This one, move a little bit away from ideal, and it is considering now the core loss components. So maybe what I should have done is put question 4B first. Maybe next year. All right. So there are some questions there for you to practice. From the Bird and from the Hughes. So you can practice those. You should be able to do these based on what we have done today. And you can look for other similar problems to these and try work them also. All right, so the big hint is that you should be reading chapter 20 from the Bird and chapter 34 from the Hughes. All right, so next week we will do the tests. We'll try to start as early as possible, 5 o'clock. So you log in and we take it from there. I will.
Yes, sir. Just to get some clarity on the email you sent about the submission of the log. You said all labs are due 2 weeks after everyone complete the first 3 labs.
When did I don't remember what I said. All right. Yes. I'll maybe what I need to do now is to make a clarification. So all right. So lab number one will be due next week Friday. All right. So next week Friday would be the 26th. So lab number one will be due on the 26th. All right.
Sir, the 26th is this Friday, sir. So it will be
It's not. Oh. All right. So the 5th then, the 5th of March.
So, sir, is it that we submit the hard copy?
Yeah, upload. Yeah, man. That yes. No, I would prefer. How would you submit the hard copy?
I guess we drop it off again, but I guess uploading is the best option.
All right. Anybody have problems uploading?
No, sir. We'll scan
No, sir,
and
not
upload,
that.
sir.
All right. Yeah, because if you do that, I can I will accept it. If you feel so you have to drop it off, you can do that too. All right. But if everybody have it at one place, I don't have to go all over the place searching for it. So if you put it in the classroom, that's all right.
Sir, upload is fine, sir, for everybody. I should think.
Okay. All right. So yes. So it is due next week Friday, which is the 5th of March. Lab number one. All right. And then maybe maybe a week after that, but I will give you more details on that. Lab number 2 and so on.
Sir, one question about the test, sir. Will it be everything up to the topic before this or including this topic?
I guess it depends on what how I feel in the morning when I wake up, the morning of the test.
Sir, no, sir, you can't do that.
Huh?
Yeah, you can't do that, sir. That'll give us some parameters to work with.
Oh, but didn't I?
Yeah, you said up to you said this class wouldn't be included.
Oh, so you have some parameters?
That's what you said initially, but I'm not sure if it's changing your mind.
No, I'm just surprised that somebody asking me the same question. You know, we spent maybe about 5 minutes talking about it already. So you know, that's why I was answering like that.
But sir, a concern of mine, sir, is that sometimes they give us a question and it takes, if one question takes like an half an hour or so.
Say that again?
No, so sometimes they give us a question, sir, and it takes like an half an hour or more or a little less. So I'm wondering like an hour to complete from unit 1 to 3 might be a bit.
Oh, don't worry about that, man. Yeah, whatever I give you to do in the hour, you'll be able to do it. I don't give you anything before I do it myself.
Okay.
And make sure that you can do it in the time.
What's the duration it is?
Somebody answer him.
One hour.
1 hour, 1 hour.
Sir, remember that when you're working out the question, you know, anytime you finish, anytime you take food with you, every time it's by 1.5, you know, for us.
All right, 2.
Well, somebody asking me about all those who have missed the lab, what happened to them? If they have to submit by next week? Yeah. Yeah, the answer is yes. You see, everybody has been scheduled. I think there was only one person who actually told me he was sick before the lab. Another person who had some work situation. But they communicated early so that to let me be aware that they couldn't be there. But everybody else had opportunities and didn't, for whatever reason, didn't use them. So they won't be getting any more special treatment. Somebody said, I said I was going to reschedule. I've rescheduled persons and they still haven't turned up. But we can't keep running after people. I can't keep running after you. You would miss it and then say I should reschedule you. Things don't work like that. So lab 1 is due next week, Friday, March
Sir.
5.
Sir.
Yeah.
Sir, I am the one that told you that I was sick, sir, and I couldn't make it. And you said you said it for me, sir. And you haven't, so that's why I'm stating.
All right. So when I tell you that the lab due?
You said next week, Friday, sir.
Okay. All right. So there's one more lab class before that time. Maybe you would want to make sure that you do it that time, right?
All right, sir. So, all right.
All right. Any other questions on that or anything?
Yes, sir. What about me, sir? For the reschedule. So we can still submit the lab Friday, sir. And then
who is
the
we?
lab in the session that's coming up.
I'm not following that question.
Oh, I am asking if we do the lab in the session coming up and still submit Friday, will it still be graded?
I don't understand that question.
Oh, sir, I mean, tell her, I emailed you about a query.
No, I don't understand, because if you ask, if I told you that is going to be, the deadline is next week, Friday, then why, if you submit it next week, Friday, I wouldn't mark it?
Never mind, sir.
Sir, you said you would reschedule me, sir, and I was not on the list, the last list.
All right. Let me say it again, Mr. Nelson. There's one more lab session before next week, Friday.
Okay.
You understand?
Yes, sir.
All right. All right, any other questions?
Sir, did you send the solution for the homework, sir?
Which
The
homework? Today?
assignment that we did.
Today?
No, the assignment that we did, sir.
I'm not sure if I did. You can check in the classroom and see. Sometimes I don't remember exactly what I'll have to go back and look. If you don't see it, just send me an email, and I will put it up there.
Sir, I don't see it, sir.
All right. All right. So I'll put up that.
Thank you, sir.
All right. All right, everybody. Let's call it a night here.